So let's continue our lecture. This is the second part for the input modeling lecture that we are discussing the parameter estimation for our distributions. And this example is the example we discussed in class for when we are looking at how to identify a distribution from a histogram. So as a review, in this example, we are counting the number of vehicles arriving at an intersection between 7 in the morning and 7:05 in the morning. And we collected information on, I think was 100 different days, 100 different days. So now we're going to use the same information to test that hypothesis that we made in terms of saying that this histogram follows a Poisson distribution. Okay, so we're going to see if our assumption is correct based on this statistic test. So we start by writing down our hypothesis. So the first hypothesis, the null hypothesis, is this random variable is Poisson distributed, and our alternate hypothesis is the random variable is not Poisson distributed. Okay? So for the Poisson, we need to estimate the parameter for alpha or lambda, which is the mean rate. So for Poisson, we need parameter alpha hat, and based on the information in the table, we know that we can estimate that parameter using the average mean. Also, for the Poisson, the probability of x being equal to x is going to be equal to this formula that you already know, x bar. Okay. Now, as an observation, remember that the suggested minimum of number of observations per bean should be greater or equal to 5. So the suggested minimum number of observations per bean has to be greater or equal to 5. And for this case, we need to compute the number of degrees of freedom. So the degrees of freedom is going to be equal to k minus s minus 1. And we're going to use alpha equals 0.05. This alpha is the confidence for our test. It's not the parameter for the Poisson distribution. Okay? I don't want you to get confused. So in order to solve this problem or use the chi-square test, I'm going to show you how to perform this test using Excel. So this file that I'm going to show you here, this is available under the 424 folder in the shared drive. So if you access that folder, you should be able to access this file. And what we have here is just a table that contains the information from the problem. So this first table has the information that was presented in the problem. So we have the frequency for each number of arrivals per period. Excuse me. And the first thing that we need to do is to estimate the parameter for the distribution that we are testing. So again, as I mentioned, we need to compute the value for the sample mean in order to estimate the parameter for the Poisson. So using that information, I was able to compute the sample mean, which is 3.64. And now we're going to use that information to compute the probability using the Poisson distribution. So again, our random variables are here. You can have either 0 arrivals during that time period, 1 arrival during that time period, 3 arrivals, and so on, up to 11, based on the information we collected in the example. And using that information, we can compute the probability of having 0 arrivals, 1 arrival, 2 arrivals using the Poisson. So if you look at this, what I'm doing in this cell is to compute the probability using the Poisson of having 0 arrivals. So we have X, which is our first, the first information that the formula asks you. We also have the mean, which is what we computed already here, the sample mean. And we want to get the probability mass function, not the cumulative probability. Okay, so we want the probability mass function. Remember, we are using a discrete distribution, which is the Poisson. So for the Poisson, instead of having the probability density function, we have the probability mass function. And this is for all the discrete distributions. So the formula asks you if you want the cumulative value or if you want the probability mass function value. So in order to get the probability mass function, we need to type false for the cumulative part. Okay, if you want the cumulative distribution, then you need to type true. Okay, so what we have, we're computing the information, we're computing the probability of having 0 arrivals for the Poisson distribution. We need the parameter, which is the sample mean in this case for the Poisson, and we need the value of the random variable. So for the first case is 0. So that probability of having 0 arrivals equals, based on the Poisson, equals 0.026. And we can extend this formula for all those cases. So we have the probability of having 1 arrival is 0.096. Excuse me. The probability of having 2 arrivals is 0.174, and so on. Okay? Now, we need to compute the expected frequency, and we're going to use these probabilities that we just compute to get the values for the expected frequency. So what we're going to do is, we know the probability based on the Poisson for 0 arrivals, and we know that we have n equals 100. We have 100 observations. Okay, so if you go here and sum this, you'll see that you have 100 observations. We collected 100 observations. So the expected number of observations, again, let me refer back to the notes. The expected number of observations, if you go back to here, for a discrete the expected number of observations, and for the continuous as well, is n times the probability of that random variable. So we have n equals 100. So what we have to do is to multiply n times, so n equals 100, so the expected for x1 is going to be equal to 100 times 0.26, which is right here. Okay, and you do the same thing for all the random variables. So 100 times 0.096 is 9.556, and so on. Okay? Now, remember the suggested minimum for each class interval. So now we need to check that we have at least 5 observations for each class interval. Okay? In order to satisfy that condition, that the suggested minimum for our class intervals is 5. So if you look at the first random variable, you notice that that value, 2.62, is less than 5. So in such type of cases, you need to combine that cell with the next adjacent cell in order to be able to satisfy the condition of having at least 5 observations in your class interval. So what we're going to do here is we're going to sum these two, and that's equal to 12.181. Then for the next one, we satisfy the condition that's greater or equal to 5. So we only have to use this. Same thing for the next one. Same thing for this one. And for this one. But now, when you get to this point, you'll see that the next class interval is not satisfying the condition. So you have to combine 4.4 and 2.0. But what's going to happen is, once you combine those two, the other 3 will not be able to satisfy the condition by themselves. So you need to combine them all together. So when you combine them all together, the value is 7.621. Okay? So now all of them satisfy the condition of having at least 5 observations per class interval. And we have 1, 2, 3, 4, 5, 6, 7 class intervals. Okay? Now we have to compute the observed frequency. In this case, that information is already provided by the problem, so we are just copying that information here. But since we combine some of the cells for the expected frequency, for example these two, now we have to combine those cells as well for the observed frequency. So for this case, when you combine these two, this equals 22. Then you have 19, which you don't have to combine, 17, 10, 8, 7, And since you combine the last 5 cells, now you have to combine them for the observed frequency as well. So this is 17. Okay, so now that you have all the information from the data points and also from the parameters that you estimated and from the probability of the distribution that you're using, in this case, the Poisson, you're computing the expected frequency based on your data points. You're trying to satisfy this condition of having at least 5 observations per class interval. So you need to combine some of the cells. That's what you did here for the expected frequency. You're combining these 2 and these 5 to satisfy that condition of having at least 5 observations per class interval. The observed frequency was already provided by the problem, but you need to combine those cells as you did based on the expected frequency. So if you combine these 2, you will have to combine those 2 as well. And same thing here, since you combine these 5, you have to combine these 5, and that gives you 17. Using that information, now you can compute the test statistic for the chi-square. So you have the observed minus the expected square divided by the expected. So you have this number minus 22 squared divided by the expected, which is 12.18. And you do the same thing for all the class intervals. When you add them together, then you have your chi-square estimation. So this is your observed chi-square. Okay? And using that information, so you have chi-squares observed, you can look at the table and get the tabulated value for the chi-square. And since the observed chi-square is greater than the tabulated, then you can reject the null hypothesis. So this data, based on this chi-square test, is telling you, the test is telling you that this data is not distributed Poisson, or the best fit for this data is not the Poisson distribution. Okay? So let me go back to the slides. So on the next slide, we have the same discussion. So we are testing the random variable if it is Poisson or not. Then we look at the observed frequency, the expected frequency. We combine those expected frequency that does not satisfy the minimum for the not observed number of observations for the interval. So remember, it has to satisfy the minimum 5. And then we compute the observed chi-square, which is 27.68. We are going to use, we have to compute the degrees of freedom for this case. So remember, it's k minus s minus 1. Since we have an estimated value, which is x bar in this test, s is going to be equal to 1. So we have 7 in class intervals. So we have 1 here, 2, 3, 4, 5, 6, and 7. And minus 1, so we have 5 degrees of freedom. And using that information, you can get the information of the tabulated value of the chi-square, since our observed value is greater than that value. Then we can reject the hypothesis. Okay? Now, the example that we discussed is for a discrete type of distribution. Now I'm going to discuss a case in which you are testing for a continuous distribution. And in this example, we have the live test performed on a random sample of electronic components at 1.5 times the nominal voltage and their lifetimes in days was recorded. So we have the lifetime of these components, and we are trying to test if these components follows a exponential distribution. So we have the random variable is exponential distributed, and your alternate hypothesis is the random variable is not exponential distributed. Okay, and that's what we want to test. So we have these data points for the lifetime of the components, and we have also the histogram. So as you can see, this histogram has a shape that looks like an exponential. So we can basically assume or have an hypothesis that these histogram or these data points can follow an exponential distribution. So the first thing we need to do is to compute the parameters. But in order to get to that point, I'm first going to explain how to perform the chi-square test for the continuous case based on this example. So to perform the test for a continuous case, to perform the test, the endpoints of the intervals must be found. So now we cannot assume that each random variable is an interval. Remember, that was only for the discrete case. For a continuous case, now you need to find the endpoints for the intervals. Okay? And these endpoints needs to have equal probability. Okay? The number of intervals k should be less than or equal to n over 5, and with n equals 50, k should be less than or equal to 10. So for this case, we are going to use, and again, this is going to be decided by the modeler. So we're going to use, let's use k equals 8 for this particular case. So then each interval will have a probability p equals 1 over 8, which is equal to 0.125. Okay? So to compute the endpoints, we use the CDF of the exponential. So remember, this is, we are trying to test our data points to see if they follow an exponential distribution. So this is why we are using the exponential in this particular case. We use the exponential distribution f of ai equals 1 minus e lambda ai, where ai is the endpoint of the ith interval. Okay? So since the cumulative distribution evaluated in AI is the cumulative area from 0 to AI, f of AI equals I times P. So we can have I times P equals 1 minus e to the minus lambda AI. I forgot to put that minus here. And you can solve for AI. You can obtain the following expression: 1 over lambda, the negative of 1 over lambda, times the logarithm of 1 minus I times P. Okay? Now I'm going to add an extra slide because I'm running out of space here. So what I'm going to do now is, using these steps, I'm going to compute the first class interval for this problem. And the first thing I'm going to do is to compute the parameter that we need for the exponential distribution. Okay, so let me add an additional slide here. Okay, so for the exponential, you need to compute the value of lambda hat. So based again on the table that we discussed at the beginning of this lecture, in order to estimate that parameter, you need to compute the sample mean, and then 1 over the sample mean is going to give you the value of lambda hat. So for this case, we have 1 over 11.894, and this equals 0.084 per day. Okay, So now in order to get a 1, we can substitute these numbers. So we have minus 1 over 0.084 times the logarithm of 1 minus 0.125, and this is I times P, which is equal to 1 times 0.125, and this is going to be equal to 1.59. Okay, so the first interval for our chi-square test goes from 0 to 1.590. This is our first interval. So if you perform the same computations for the next 7 intervals, you have for I equals 2, 3, 4, 5, up to 7, you have a 2 equals 3.425, a 3 equals 5.595, a 4 equals 8.252, 5 equals 11.67, a 6 equals 16.503, a 7 equals 24.755. Okay, and using these values, now we have the intervals for our chi-square test for the exponential. And remember, these intervals, all of them have the same probability. So using this information, let me look for So using this information, what we just did was to compute the first class interval, which is right here. And you can do the same process to compute the next class intervals. And then once you have those class interval, the procedure is the same. You look for the observer number of observations and also for the expected number of observations for each class interval. And using that information, you can compute the observed chi-square, which in this case is 39.6. And by comparing that against the tabulated value, you can reject the null hypothesis because the observed value is greater than the values tabulated for the distribution. So in conclusion, this distribution does not follow an exponential distribution. Okay, so let me summarize that right here. So we have chi-square observed equals 39.6. Remember, in order to get the expected, you're multiplying the number of observations times the probability. Since we have 8 intervals, we have the probability is going to be 1 over 8, which is equal to 0.125. So this is 6.25. We have the degrees of freedom are going to be equal to k minus s minus 1. We have one parameter that was estimated. We have 8 intervals. So it's 1 minus 1, and this equals 6. we are using alpha equals 0.05, so the tabulated value for 0.056 equals 12.6, and chi-square observed is greater than chi-square of 0.056, so we reject our null hypothesis. Okay? So we have one more thing to cover to complete this lecture, and it's the KS test for these type of problems. So as you remember, we use the chi-square test and the KS test to test our uniformity for the uniform 0, 1. What we are doing now is, instead of testing just for the uniform 0, 1, we are using the same test procedures, but to test for other distributions. Okay? So now I'm going to show you how to use the KS test to test for other distributions. So as an intuition, this KS test formalizes the idea behind the examining a QQ plot. So from chapter 7, you remember that the test compares the continuous CDF, f of x, of the hypothesized distribution with the empirical CDF of the n sample observations. Based on the maximum difference statistic, this D, which is the difference between the maximum f of x minus the empirical evaluated in x, we made a conclusion based on that. So this is a more powerful test, particularly useful when the sample size is small, and also when no parameters have been estimated from the data. Okay? So next, I'm going to show you an example. So suppose that 50 interrogable times in minutes are collected over the following 100-minute interval. So we are looking at a 100-minute interval, and we are collecting the interrogable times for these entities. And they are arranged in the order of occurrence. So we want to test if these interrogable times are exponential, or if the interrogable times are not exponential. Okay? We're going to use a confidence of 0.05. So we can compute our tabulated value for this. Since we're having 50 observations, if you look at the table, in order to get the estimated value or the tabulated value, for the KS, I apologize for how the table is presented. But if you look at the table, if you have over 35 observations, then if you have over 35 observations, then for 0.5, for your 0.05 alpha, you need to use this formula. So that's what we're going to use. So for this case, we have, for the 0.05, we're going to use, this is going to be equal to 1.36 divided by the square root of n, which is going to be equal to 0.1923. And now we have to get the value from the chi-square test to compare again against this one. Okay? So something that you need to know in order to solve or in order to apply the chi-square test for this example is the following. So it can be shown, let me add another slide here. So it can be shown that if the underlying distribution of inter-arrival times say T1, T2, and so on, is exponential, the arrival times are uniformly distributed from 0 to t. Okay? So the other thing that you need to know is that we're going to have to normalize the arrival times to a 0-1 in order to apply the KS test. So the arrival times are then normalized to a 0-1. So the KS test can be applied. Okay, so let me show you how to solve this problem. So again, we are testing to see if these data points follow, or the interarrival times follow an exponential distribution. But what happened is we cannot apply the KS test directly for the exponential. So what we are doing in order to use the KS test to test for the exponential is to use a fact, that is the one that is I'm writing on the first bullet, that we know that the underlying distribution of interarrival times is exponential. Then we know that the arrivals times are uniformly distributed. So what we are going to do, instead of testing for the interarrival times and check for the exponential, what we're going to do is we're going to test for the arrival times, not the interarrivals, the arrival times, to check if they follow a uniform distribution. Okay? But in order to test for that, we need to normalize those data points so they can be within 0 and 1, and we can apply the KS test as we did for the uniform 0, 1. Okay? So I'm going to show you that here. And again, you have access to these tables. So we have the 50 interarrival times, and we have them right here. in the order in which they were presented in the table. And what we're going to do is we're going to use those inter-arrival times, and we're going to get the arrival times for each entity. Okay, so we go here 0.44. So we put 0.44, and then we add 0.53 to get the second arrival time. We add 2.04 to get the third arrival time, 2.74 to get the fourth arrival time, and so on for all the data points up to 50. Okay, so the last arrival occur at the minute 99.29. So remember, we are looking only at 100 minutes. So now we have that information of the arrival times. We know that the arrival times follow a uniform distribution if the underlying distribution is exponential. So we're going to normalize those data points in order to get values from 0 to 1. Okay? So in order to normalize these numbers, we need to divide each number by the total minutes, which is 100. So we divide 0.44 by 100, 0.97 by 100, and so on for all the data points. So we normalize them, and all of them are within 0 and 1. Okay? So now we can use these numbers to test for uniformity. Okay? And you know how to proceed for the test. You need to find D minus and D plus. So D minus is 0.019. D plus is 0.1054. So our D is 0.1054. Since this is less than our tabulated value, which is 0.1923, then we do not reject the hypothesis. Okay? So let me go back here. And write that down. So we compute D, and that is equal to 0.1054. So H0 cannot be rejected. Okay? So with this example, we complete the material for the input modeling topic. So in this chapter, we describe the 4 steps in developing input data models, which are collecting the raw data, identifying the underlying statistical distribution, estimating the parameters, and testing for goodness of fit. Okay? So the next thing we're going to do is to show you how to use a input modeling software to see how the topics or the concepts that we learn in class can be used when you have a complete set of data points, and how you can select the best distribution based on the information provided by the software. Okay? So we're going to have a homework for this chapter, and I'm going to post those details on e-learning. Thank you.